So good morning in parts of Canada, good afternoon in other parts of Canada today, and welcome to this PIR live event webinar. We're brought to you by Partners in Research Canada. My name is Stacey Joyce and I'll be your host. Remember that you can ask questions anytime by clicking chat near the top left of your screen and typing your questions into the chat window. I will relay these questions to our guests during the question and answer period. If you include your name, school, and city, we'd love to give you a shout out when we ask your question. Today's guest is Valerie Chiykowski. She is a PhD candidate in the Department of Chemistry at the University of British Columbia. Thank you so much for joining us today. I'll let you take it away. Oh, just one moment, Valerie. There we go. Now you can take it away.
Hi, everyone. I'm just going to get my presentation going.
Perfect. Oh, there we go.
So as Stacey said, my name is Valerie Chiykowski, and I'm a PhD candidate in the Department of Chemistry at the University of British Columbia. So I went to university for my undergraduate degree at Queen's University in Kingston, Ontario. And when I started, I didn't actually know I wanted to be a chemist yet. I thought I was going to be a doctor, but I remember on my first day of classes in first year, I fell in love with chemistry. And so I studied it for the next 4 years to get my degree. And then when I graduated, I still wasn't done learning about chemistry. So that's when I moved to Vancouver. I started my PhD or my doctorate degree in chemistry. So technically I am still a student, but if you add it all up, I'm actually in grade 20 now. So my days aren't spent going to class so much as they're spent doing research experiments in laboratories and helping teach across campus. So I conduct my research in the group of Dr. Curtis Burlingame. And there we focus on studying solar cells and solar fuels. So trying to understand them better and also make them much more efficient. So what is a solar cell? Well, we often call them by their scientific name, and that's photovoltaics. And if you break down the word, it actually makes a lot of sense. Photo means light and volt means electricity. So these are just technologies that convert light energy into electricity. So there's many types of solar cells, lots of different technologies. They all use different materials, different processes, and they have different advantages and disadvantages. But the type of solar cell that we focus on is called a dye-sensitized solar cell. So this means they use dye molecules, just like the dye you might use to tie-dye your clothes or dye your hair. Dyes like that, which are excellent at absorbing sunlight. So the whole process begins when the sun, which we all know is very powerful. Think about standing outside on a hot day in the sun versus in the shade. You're much warmer in the sun where the rays of sunlight can hit you. So the sun shoots down its sun rays, which a dye molecule can absorb. So typically we try to work with the darkest dyes possible, something as close to black as possible. If you think about, again, standing outside on a hot sunny day, if you're wearing a black t-shirt, you're typically much hotter because it's absorbing lots of the sunlight compared to a white t-shirt. And actually some people have extracted the dyes in fruits like blackberries and raspberries, like really darkly colored dyes, and actually use them for functioning solar cells. So after the dye absorbs the sunlight, it gets really excited. And this is actually a scientific term we use to mean full of energy. And if you remember in science class in particle theory, you'll remember everything is made of protons, neutrons, and electrons. So when our dye is excited, it's able to lose one electron into this electron collector. At this point, that electron can enter our circuit and we get electricity because all electricity is electrons moving through a wire. So this allows us to turn on our light bulbs, charge our cell phones, whatever we need electricity for. After that, the electron returns back to our solar cell. Now another component of the solar cell is needed, and we call that the Electron Shuttle, and it carries our electron back to our dye. So now our dye has all of its electrons again. And at this point, the whole process can continue again and again, and we can generate continuous energy. So just to give everyone an idea of what we do in the laboratory versus what you might imagine in the world, when a lot of people think of solar energy, they think of those big solar panels that are on buildings or the roofs of houses, or maybe even what we call solar farms that stretch miles and miles of solar panels. Well, actually, each solar panel is made up of many solar cells, and we study one solar cell at a time. So I've shown a solar cell that we've made in the lab on the right there, and the actual functioning part of the solar cell is that dark dot in the middle. And it's roughly the size of the fingernail on your pinky finger, so quite a bit smaller than you might have imagined. And what we do in our experiments is we'll change one little aspect of that solar cell, and then we'll see how that affects how much electricity it can generate. So our current research, some of the projects we're currently working on, one of them is to make these solar cells more stable, because one of the biggest disadvantages of this one technology, the dye-sensitized solar cell, is that they tend to be a little less stable than other technologies. One major problem is that the dye falls off the surface of the solar cell, and when it does this, it's not as effective at absorbing sunlight or giving up its electron to the circuit to make electricity. So we're working on ways to make sure that that stays in place a little better. Another thing we're studying is interaction of different components of the solar cell. So in the animation, you saw that Electron Shuttle carry the electron back to our dye molecule. It's really important that dye molecule is attracted to that shuttle, that those two pieces come together like a puzzle piece, and that they fit well together. So we study different interactions and different bonds between these components and make that shuttle more efficient. So in our laboratory, it's really important as scientists when we're doing experiments that we get good reproducibility of results. So this means that we can get the same result again and again. Once we make our hypothesis, we can prove whether it's true or false before we share it with the rest of the scientific community. So here's an example of 12 cells on the left, 12 solar cells that have been made, and they should all be identical and have the same performance. And if you'll notice, that black dot in the middle that I said is the active part of the solar cell is quite dark, almost black. So that's an indicator that it's an excellent light absorber. So we'll carry out lots of trials, and then we'll use what we call our solar simulator. So it's basically a really powerful light bulb. It's like a fake sun. And we shine the light on our solar cells, and we see how much electricity it generates. So here's a photo of myself and my supervisor, and we're testing a solar cell. And the light is actually so bright that we have to wear tinted sunglasses as to not damage our eyes. Just like if you're out on a sunny day, you wouldn't want to stare directly at the sun. But the main problem with solar energy is that you can produce electricity during the day when the sun is shining, but a lot of us need to use electricity at night when we come home and cook our dinner after dark, watch TV before bed. So the one solution to this is to use the electricity while it's being generated during the day while the sun is out to make a fuel. That fuel will store energy, and we can use it later when the sun isn't shining. So that's where we get the name solar fuel, because we use electricity from the sun to make the fuel. So our group makes fuels from one of the most abundant things possible, and that's water, or H2O. And what we do is we split water into hydrogen and oxygen gas. So oxygen is what we breathe, it's not harmful at all, and hydrogen is what can be used as a fuel. So just like we might fill our cars with gasoline or diesel fuel, many cars are starting to be run on hydrogen fuel now. The one problem is that to make hydrogen and oxygen from water, it requires quite a bit of energy, and we call this an energy barrier. You need to put a significant amount of electricity in to get hydrogen and oxygen out. So one thing we do is develop catalysts, and these are things that change the process slightly of how we get from A to B, or water to hydrogen and oxygen, that requires less energy and less electricity. So our group has actually developed a really new, easy way to make these catalysts just using light. So we dissolve our starting material in a solution. We drop it onto whatever we want. We can put it on metal, plastics, glass, foam. We then put it under a light bulb for a couple hours, and this will change the composition of our starting material to become the catalyst. And at this point, we study how effectively our catalyst can split the water into hydrogen and oxygen. This has gotten a lot of attention from industry because it's a really new, exciting way to make these catalysts very easily. So this is an example of my colleague Danielle. She has put the catalyst onto, or the starting material rather, onto a piece of glass, and she's going to be putting that glass under the lamp. So we use two types of lamps for this. That's an infrared heat lamp. So if any of you have reptiles at home, you might use a red heat lamp to heat their terrariums. So we use those lamps, or UV or ultraviolet lamps. So if you've ever been to glow-in-the-dark laser tag or mini putt, and there's been those purple light bulbs that turn your teeth or your clothes all glowy, we also use those kind of light bulbs to make our catalysts. All right, so as a PhD student, I come to work every day from 9 to 6. It's kind of like a job, and I work with this team of scientists. So we've got chemists, engineers, computer scientists, physicists, and we're all working together trying to solve these research questions about how to make solar fuels and solar panels more effective and efficient. So on behalf of the whole team, we just want to thank you for listening to our research, and I look forward to answering any questions you have about it.
Great. Thank you so much for your presentation. That was really easy to follow. I certainly learned a few things already. Just remind everyone that you can ask your questions using the chat function. There's a chat button towards the top left of your screen. That should give you a chat window, and near the bottom of that window, you can select to send that message to everyone and type your question in there. That way our students can see what other students want to know too from across the country. So the first question I have for you, Valerie, is you mentioned that you use dyes as dark as possible to absorb more light. So you mentioned black as an example, but when I look around and see a solar farm, for example, the solar cells look dark blue. Is there a reason why they would be blue instead of black, or is that something else that's making it look blue?
So that could be two factors. One of them is possibly they use a special, excuse me, a special conductive glass on top of the solar cell. So that could be tinted blue, is one guess. And that helps filter ultraviolet light out, so we just get visible light. So ultraviolet light, the reason why we wear sunscreen is to protect against really harmful ultraviolet light. So that light can also be harmful to solar cells, so sometimes an extra coating is used to block out that light. That's
Okay.
probably the blue that you're seeing.
Okay. And I've got a question that just came in here. Is solar energy generation different in Canada and other northern climates versus areas closer to the equator?
That's a really good question, and it absolutely is. There's certain solar cells that work better with very direct sunlight, and they require a particular angle of sunlight to work the best. And these are called crystalline silicon solar cells. And that's what you'll see in California, in the desert, much more common there. And they work really well there, but they wouldn't work well somewhere like Vancouver, that's quite rainy all the time. We don't get that direct sunlight, or in northern climates where the angle of the sun is much different. So that's where something like the dye-sensitized solar cell, the whole other technology, would be a lot more effective.
Okay. And is the dye-sensitized technology commercially available right now, or is it still in development?
It's commercially available. You'll actually see, because it can be put on flexible substrates or flexible materials, it can be used a lot if you see like a backpack with a solar panel on it. I've seen a couple of those around. Those are probably dye-sensitized solar cells. The alternative, crystalline silicon, because they're made of crystals, they're quite rigid, and so they can't go on fabrics. So the dye-sensitized solar cell is really good for that. And also you might see them on calculators, the little solar panel at the top, because these solar cells are so good with indirect light or dimmer light. They're often used for indoor applications, so electronics that have solar cells in them.
I had never thought about that. Those have been around for a long time.
Yeah. The dye-sensitized solar cell was first discovered in 1991, so it's been around for quite a few years now.
Huh. All right, well, the next question I have is, you talked about a separation between the dye and the electron acceptor. What would cause that separation?
A lot of things can cause it, and the most damaging is water. So we try to make our cells so that they have a really good seal. You would never want water leaking in, but if it does, that water can cause the bonds to break between the dye and the electron acceptor. So you have to work really hard to A, make sure that there's no leaks, and B, make sure that when you're assembling the solar cell, it's done in a really dry room with a low humidity, or else water gets trapped in and it can help take that dye off.
Okay. And then you mentioned that you have been investigating some shuttle molecules to try to keep the dye onto the electron acceptor. How do you investigate how well that shuttle molecule fits or how effective it is at keeping the dye in place?
So we can do it a couple of ways. One is when we're designing the components of a solar cell, we model them using really insane calculations. We actually have to type out our calculations and let the computer work on it for a couple days, and it basically models the molecule so that it predicts its shape, and then of the dye molecule and of the electron shuttle, and then in space on our computer we can see how well they fit together. Another thing we can do is just consider things that we've learned throughout our chemistry careers, things like hydrogen bonding, what holds water molecules together when it turns into ice. We're currently looking at how that can affect how well the shuttle and the dye are attracted to each other. And then in terms of investigating it, the dye molecule looks quite different when it's without its electron. So after it's given up its electron to make electricity, and before that shuttle brings the electron back, it looks very different than its state when it has all its electrons. So we can study the difference and see how long it's without its electron before that shuttle brings it back.
Okay. So kind of a more application question of solar energy. When we talk about using clean energies like solar and wind, we think that that will offset gas emissions, but there is a component of emissions in manufacturing those technologies. So is producing solar cells efficient enough to offset the emissions that are created during their production?
Yeah, right now the payback, so the amount of time it takes to produce energy with a solar panel before you get all the money you put into it, is still 10 years, or actually I think it's come down a little bit in the last couple. So I'd say 8 to 10 years. So it still takes quite a bit of time to pay off all the costs you put into making the solar cell. And that does include some of the environmental impacts of making the solar cell. That's all included in that calculation of 8 to 10 years. So that is a consideration, and they are getting much more efficient at making them. So they are still a renewable energy, and I think that in the end they contribute to global warming a lot less than the combustion of our non-renewable fossil fuels. So overall, I believe that they are much greener than a lot of other energies.
And so 8 to 10 years to sort of get that payback. How long are current solar cells expected to be effective? What's their lifetime in practice?
Yeah, so that's a number that changes a lot depending on the solar cell technology. So the crystalline silicon solar cells, which I mentioned are in some of the hotter climates near the equator, those now have warranties up to 25, 30 years. So they've really, really improved the stability of those solar cells. The dye-sensitized solar cell tends to be a little shorter, maybe 15 years with outdoor applications and a lot longer for indoor applications. So it's really technology-based at this point.
Okay, great. So I have a question now from Ms. Rahman. Is there any thought about making solar energy generation mandatory in new buildings, be they commercial or residential? Just talking about flat roofs in particular that could be utilized for that.
I think at this point in time, there isn't quite enough legislature or rules that enforce solar energy, and there could even be more done to help people pay for the solar panels on their roofs. So unfortunately, right now, there isn't a lot of incentive for people to put them on. But as people get a lot of pressure from clients and consumers to be more environmentally friendly, it is becoming a lot more common, and you see a lot more green architecture firms popping up that do design all of their buildings so that they are the perfect angle.
Oh, we've just got you frozen there for a minute, Valerie. I'll just give you a minute to pop back on. Might just need a minute there. Technical difficulties. Thanks for hanging in there. I'm just going to give Valerie a moment in case she was disconnected so that she can connect back to us. We do have a couple more questions to get to and a bit more time to do so. In the meantime, I can let you know that next week we've got another live event coming up. And that event is Problem Solving with Code. That'll be September 28th at 1 p.m. Welcome back, Valerie. We lost you there for a quick minute.
Sorry.
No worries. It does happen with internet connections occasionally. So I do have another question for you here. If someone wanted to be a researcher in the field of solar energy, how would they prepare themselves? What classes or fields should they pursue? Is chemistry the only option, or do you often work with individuals in related fields to bring it all together?
Yeah, I work with a lot of different scientists. As I mentioned, in our group alone, we have chemists, we have some physicists, chemical engineers, mechanical engineers, computer scientists. So all these people would have gone to undergrad, and myself have gotten their undergraduate degree and really whatever they love the most. So for me, it was chemistry. And then throughout my undergraduate degree, I tried to get involved as much as possible in different research labs. So each of my professors would have led one research lab. And so I would have tried to get involved in the summer or after class to get research experience. And then from there, if you have good enough marks, but mostly just like a lot of enthusiasm for science, then you start to apply to graduate school where you pick a research that you're most passionate about, and then you study that almost full time once you start your degree.
Great. And so you mentioned that you fell in love with chemistry more in first year university. Before that, you thought of sort of the traditional path to being a medical doctor. What is it about chemistry that you fell in love with?
I just think it explains everything. So all the things that I was learning in biology about healthcare, it all came down to the chemicals and the molecules reacting with each other, which I just found so exciting, that we could try and see down to such a small scale and how everything works and fits together. So that was what really excited me, and it still excites me.
Well, that's good because it sounds like you spend a lot of time each day with chemistry. So a couple more questions that we have time for. We haven't talked a lot about the solar fuels. You mentioned them in your presentation and explained them. Are solar fuels dangerous to store at all? Oh, it looks like we have frozen again briefly. Ms. Rahman mentions that she wishes her last year's chemistry students had heard the comments about falling in love with chemistry. I definitely hear you on that one, but hopefully this year's students will be able to watch this recording and hear about Valerie's passion, which is certainly shared by many other people in the field.
Sorry about that.
No worries. So the question that I was asking you just as you froze there was, are solar fuels dangerous to store, and how do you try to mitigate that if the answer is yes?
That's also a really, really good question. Hydrogen fuel does have some safety concerns associated with it. It is fairly explosive. And because it's a gas, it's pretty hard. It's a lot more difficult to store than something like a liquid or a solid fuel. So a whole bunch of other research groups are currently working on studying the safest way to handle them and also the most efficient way to store them, how well you can compact them, stuff like that. So it is really important to study the safety of these things, because if we are trying to change all of our infrastructure and try and change buildings and homes and cars so that they can be run on hydrogen fuel, which can be quite explosive if treated unsafely, it's really important that we focus on that. And right now, it is safe. It's been employed a lot in a bunch of different car systems. So it is safe enough to use, but it is something we should always be thinking about when we're investigating new fuels.
Thank you. So I think we're running out of time for today. So I wanted to thank you very much, Valerie, for joining us today, answering our questions and sharing your expertise and your love for chemistry. One of our viewers was grateful and kind of wished she had been able to share your love of chemistry with last year's chemistry students. But thank you so much for your time today.
Oh, it was my pleasure. Thank you for tuning in.
And for more webinars like this one, check out our PIR live event schedule at pirweb.org. And thanks for tuning in. Have a great day, everybody. Bye now.